For millennia, we've been captivated by the idea of endowing man-made objects with souls or minds, a testament to our innate desire to see reflections of ourselves in other vessels. This universal form of projection, rooted in the ancient belief of animism, suggests that all objects, and even concepts like language, possess a distinct spiritual essence. As civilizations evolved, becoming more sedentary and forming complex societies, this belief deepened, influencing both the spiritual and daily realms. It gave rise to the concept of the human soul in Western cultures, a notion that spread widely. However, even as societies transitioned from animistic to more organized religions, the fascination with automata persisted. This interest flourished particularly in regions where scientific inquiry was encouraged, highlighting humanity's enduring paradox with artificial life. Our fascination with projecting our qualities onto our surroundings reveals a fundamental aspect of human nature, serving both as our gift and our curse. Dharmakirti, an influential Indian Buddhist philosopher of the 7th century, is renowned for his work on the theory of perception and epistemology, which examines the nature of knowledge and how we come to understand the world. His investigations into the mechanisms of cognition and the validity of knowledge offer intriguing parallels to modern discussions about how artificial intelligence interprets and interacts with its environment. Guifeng Mi, on the other hand, was a prominent figure in the development of Chinese Zen Buddhism during the Tang Dynasty. His work often bridged Buddhist doctrine and Chinese philosophical thought, particularly concerning the nature of mind and reality. Zhongmi's insights into the subjective and objective understanding of the world and his emphasis on the inherent Buddha nature in all beings provide a fascinating lens through which to view the ethical and philosophical underpinnings of artificial intelligence development. By highlighting these philosophical traditions, this narrative emphasizes that our technological advances in artificial intelligence are not merely scientific achievements, but are also deeply rooted in a rich philosophical legacy. This perspective invites us to consider how ancient wisdom can inform and shape the ethical frameworks and conceptual foundations of our modern technological pursuits. It suggests that the quest to develop artificial intelligence is not only a continuation of our desire to innovate, but also a reflection of a long-standing human endeavor to understand the nature of consciousness and reality, bridging the gap between ancient philosophical inquiry and contemporary scientific exploration. In ancient Egypt, the soul's multifaceted complexity was recognized with the Ka, denoting the vital essence, present in both humans and deity statues, enabling their participation in rituals. This period, particularly the New Kingdom, saw offerings to statues for divine advice, embodying early interactions with artificial entities. Similarly, Solomon's throne, adorned with mechanical animals, exemplifies early automaton concepts, reacting violently to unauthorized users. Hephaestus, in Greek mythology, further illustrates this, crafting automatic metal workers and sometimes gifting them to other gods. Incorporating Dharmakirti and Guifeng Mi, we find a parallel in their philosophical inquiries into the nature of consciousness and perception, enriching our understanding of these ancient technologies within a broader cultural and intellectual context. Their contributions highlight the global nature of these inquiries, suggesting a universal human fascination with mimicking life and intelligence, foundational to the development of artificial intelligence. This dialogue between ancient engineering and philosophical thought underscores the deep-rooted human desire to understand and replicate the essence of life, bridging diverse cultures and epochs in the pursuit of creating lifelike entities. Still, in the Hellenistic period, inventors created devices like water clocks, or clepsydra, that activated at specific times for various activities, laying the groundwork for mechanisms akin to the cuckoo clock. Hero of Alexandria's Aeolipoli, recognized as the first steam engine, exemplified the era's fascination with manipulating materials and energies. A notable invention, the Antiquity mechanism, stands out as the earliest known analog computer, capable of predicting planetary movements. This convergence of engineering and scientific inquiry reflects an early integration of technology with the natural world, indicative of the era's contributions to the foundations of modern computational devices. This context enriches our narrative by connecting these technological marvels to the broader cultural and intellectual environment, emphasizing the continuity of human curiosity and the evolution of our attempts to understand and replicate the mechanisms of the natural world through technology. Before transitioning to the Middle Ages, it's essential to recognize the ingenuity of ancient civilizations in creating devices capable of automated operation, cyclic movements, and predictive calculations. These early technological marvels, from self-operating machines to the Antiquity mechanism, showcase humanity's timeless pursuit to comprehend and interact with the world. This endeavor, deeply rooted in cultural imagination and intellectual curiosity, illustrates a continuous dialogue between our ancestors and their environments, underlining a profound legacy of innovation that precedes the Roman Empire's zenith. This historical reflection sets the stage for exploring how medieval advancements further contributed to the narrative of human creativity and technological evolution. By the close of the first millennium AD, the ingenious ideas that once thrived in ancient Greece had spread beyond their origins, merging with the cultural and technological landscapes of other civilizations. The Byzantine Empire, for instance, became known for its elaborate use of animal automata within the opulent throne room of Constantinople, showcasing the enduring fascination with mechanical life. Concurrently, the Abbasid Caliphate, particularly in Baghdad, saw the emergence of wind-powered automata. These devices, often resembling plants and animals, added a magical touch to the palaces, hinting at the sophistication and creativity of Islamic engineers. This era of innovation reached a pinnacle with Ismail al-Jaziri in 12th century Mesopotamia during the Islamic Golden Age. His seminal work, The Book of Knowledge of Ingenious Mechanical Devices, cataloged a series of devices designed to ease human efforts, foreshadowing modern appliances' functionalities such as the flushing toilet. Al-Jazari's contributions have earned him the title of the Father of Robotics, exemplifying the early principles of engineering that would inspire generations of inventors, including the renowned Leonardo da Vinci. Despite the marvels these inventions represented, many lacked practical application in the societies of their time. This period's technological advancements were often reserved for the elite, reflecting the economic structures that favored military strength and trade over mass production and industrial development. The legacy of these early automata, while not directly influential in daily life, underscores a period of profound curiosity and intellectual pursuit, laying the groundwork for future technological breakthroughs. Following the Renaissance, the scientific revolution catalyzed an era of profound discovery, inaugurating the Enlightenment in Europe. This period was marked by an explosion in the application and innovation of mechanical devices, ranging from precision clocks to intricate toys and advanced scientific instruments, which played critical roles in experimentation and observation. The era's intellectual ferment also fostered the conceptual separation of mind and body, a philosophical innovation of Descartes that deeply influenced the mechanistic understanding of the world and the beings within it. This intellectual backdrop facilitated the emergence of devices like the Jacquard loom, employing punch cards to dictate weaving patterns, embodying the nascent idea of programmable machinery. The evolution of these concepts mirrored developments in popular culture, particularly in speculative fiction, where the blending of scientific curiosity with imaginative storytelling highlighted society's fascination and trepidation about technology's potential. Mary Shelley's Frankenstein serves as a seminal work from this period, encapsulating the anxieties and ethical dilemmas posed by unchecked scientific advancement. The narrative of creating life through artificial means, as depicted in Frankenstein, not only captivated the public imagination, but also presaged modern discussions on the boundaries of technology and the moral responsibilities of its creators. As scientific fields became more structured and advances in mathematics accelerated, the demand for computational devices grew, leading to the Industrial Revolution's mechanized prowess. By the 19th century, the integration of machines into daily life was unmistakable, exemplified by Charles Babbage's automated difference engine and the programmable analytical engine. This analytical engine, powered by steam and utilizing a punch card system similar to the Jacquard loom, represented the zenith of mechanical excellence at the time and was the first programmable calculator devised. Ada Lovelace, working with Babbage, penned what is considered the first computer program, emphasizing the analytical engine's capacity to execute various tasks as commanded, yet devoid of original thought or anticipation. Lovelace's observation eloquently echoes the era's technological aspirations and its limitations, bridging the gap between mechanical ingenuity and the burgeoning field of computing. Lovelace also made the prescient observation that the analytical engine, while built and able specifically to process series of numbers, could, with some adjustment, be used to process symbols in general. By the 1900s, the computational landscape had vastly expanded, incorporating mechanical calculators for everyday calculations and analog computers for specialized tasks like tide prediction. This era also saw the rise of electronic computing, initially spurred by military needs, which significantly boosted research and development funds. The 1920s introduced RUR, or Rossum's Universal Robots, a play that popularized the concept of robots, reflecting societal intrigue and apprehension towards artificial labor and autonomy. Around the mid-20th century, a period of remarkable innovation and scientific inquiry, Alan Turing emerged as a key figure whose work not only played a crucial role in the outcome of World War II, but also laid the groundwork for the modern fields of computing and artificial intelligence. Turing's contributions were not limited to practical applications in cryptography, but extended deeply into the philosophical and theoretical realms, profoundly shaping the way we conceptualize and interact with computers today. Turing's most notable philosophical contribution is perhaps the imitation game, now known as the Turing test, introduced in his 1950 paper, Computing Machinery and Intelligence. This test was designed to provide a criterion for determining whether a machine could be considered intelligent. According to the Turing test, if a human interlocutor could not distinguish between responses from a machine and those from a human during a blind conversation, the machine could be said to exhibit intelligence akin to human thought. This proposition challenged the prevailing notions of intelligence and consciousness, sparking debates that continue to this day regarding the nature of mind and the potential for machines to achieve true artificial intelligence. Beyond the Turing test, Turing's theoretical work on the universal Turing machine laid the mathematical foundation for modern computing. This abstract machine concept demonstrated that a single machine could, in principle, perform any conceivable mathematical computation if it were representable as an algorithm. This idea directly contributed to the development of the digital computer and the principle that a computer can be programmed to execute any operation that can be described algorithmically, a core tenet underlying all modern software. Turing's work in cryptography, particularly his development of techniques to break the Enigma code used by the Nazis during World War II, showcased his ability to apply abstract theoretical principles to solve concrete problems. This not only had a monumental impact on the war effort, but also illustrated the practical implications of theoretical computer science. Moreover, Turing's exploration of morphogenesis in biology through the introduction of Turing patterns in his paper The Chemical Basis of Morphogenesis demonstrated his interdisciplinary approach, linking mathematics to biological processes. This work foreshadowed the modern field of computational biology and the use of computational models to understand complex biological systems. Through these contributions, Alan Turing bridged the gap between the philosophical considerations of mind and intelligence and the practical development of computing technology. His work invites ongoing reflection on the ethical implications of artificial intelligence, the nature of human cognition, and the limits of machine learning, influencing both theoretical discourse and the evolution of technology. Turing's legacy endures in the foundational principles of computer science and AI, as well in the continuing dialogue about the relationship between human and machine intelligence. By the 1950s, the transition to programmable computers utilizing vacuum tubes signified a quantum leap in computational capabilities, soon to be superseded by more efficient transistor-based systems. These advancements not only facilitated a broader commercial application of computers, but also set the stage for the rapid technological evolution that would define the latter half of the century.